Are there any questions before we begin? Okay, so just remember that next Monday we'll have another exam. It will be structured in the same way as the first exam. So it will be two parts. Each part will have like three problems. Each part will have its own upload. I'll send you like a study guide and some practice exams. I'll probably have that ready around Wednesday. So um once I have that, I'll just upload it to Canvas and send you an announcement. I think we should be done with the material for the exam either tomorrow or Wednesday. So, but it will be similar, at least in the format, it would be basically the same as the first exam. So, but yeah, I'll let you know uh, the topics and everything once I finish writing the study guide. Another thing, before I forget, about the quiz, if you remember the quiz, like from last time, the quiz, the first question was about finding the derivative using the limit definition of the derivative. So only when you like the idea is that you don't want to find the derivative of a function that way. That's why we have the rules for finding derivatives. So that's kind of like one thing that you only have to do when it says explicitly to use the limit definition. When it doesn't say use the limit definition, you can just find the derivative in whatever ways work for you. So you can use the product rule, quotient rule, chain rule, whatever. So I just mentioned this because I believe on the third question of the quiz, some of you tried to find the derivative using the limit definition, which is fine. It will give you the right answer, but it can take longer. So only when it says use the limit definition, you have to do it that way. In any other case, you can use the rules for derivatives. Okay. So that's just like an important thing to be aware of because it would save you some time. So the idea for today is to continue finding more derivatives of functions. So, and today we're going to do something that's very useful, which is called implicit differentiation. And so, what's the idea for this? So, let me give you an idea. Oops, sorry about that. Let me put in do not disturb mode. Okay, so the idea here is, let's start with an example. Imagine, oh, can you see this? I don't know. Okay, yeah, it's a little bit late, delayed, but I don't know why, but okay. So imagine that I give you an equation like x squared plus y squared equals 2. Let me stop sharing because I feel there's like a small time gap between what I'm writing. If not, I'll just connect it with the cable to see if that counts. Okay, so like imagine if I give you an equation like x squared plus y squared equals 2, which is the equation that you see here. Okay, now it's good. This, I mean, if you remember, this is the equation of a circle. So this is the equation of a circle. However, this circle is not, I don't know if you remember this, but this circle, a circle is not the graph of a function, right? Um, not the graph of a function. Anyone remembers why this is not the graph of a function?
Because it doesn't pass the vertical line test.
Yeah, so good. So the idea, correct. So for example, if you take a value like x here, if you take a value of x here, like for this value of x, there will correspond to y, to corresponding y values, which are the ones that you see here. So the idea of a function is that for any value of x, there can be at most one y value. So, but let me write that down. So it does not satisfy the vertical line test. Right? So, but still, like if you look at this circle as a curve, if you think about it just as a curve on the xy plane, it does seem look like it should have like tangent lines, right? Like so, for example, if I pick a point here, this looks like the tangent line, and here should look like the tangent line to the circle, right? So it does make sense to still try to find the tangent lines to the circle, even though it's not a function, right? So we still would like to, let's say, what's the point on this circle? Let's say could be 1 comma, in fact, let me choose a different point. Let's put this one here. So here we could have the point 1 comma negative 1, right? And we could still try to find, we can still try to find, or we would like to find the tangent line to this to the circle at that point. Still, we want to find tangent lines. Okay. So there are two options for how you can do that. The first option, so how to do this. So the first option is to actually use the equation of the circle. Let me write it as option 1. Use the equation of the circle to write y as a function of x. So again, let's just try to think about that. So you have x squared plus y squared equals 2, right? And now we are trying to see to what extent it's possible to write y as a function of x. So the idea is to solve this equation for y. So how can you solve this for y? Well, you can write y squared equals 2 minus x squared, right? If you subtract x squared on both sides. And then what can you do next to solve for y? What could you do now? Let's do like an analogy. If I told you that, here's an analogy. If I said that y squared equals 4, what would you say y is? Uh, right. And how would you say that y equals 2? What did you do to say that y equals 2? I mean, you probably are doing it in your head, right? But there's how are 2 and 4 relate? You took the square root on both sides, right? So y is equal to 2. And is there another option that's available to us here? Is that the only option, y equals 2? It could be -2, right? So in general, if you're taking like, so we would like to take, it's essentially the same idea. We would like to take square roots on both sides. It's just that when we take square roots, let me use different colors. So if you could take square root on both sides, so you get y equals 2 minus x squared. Or you could also get y equals, maybe I should do a different one here. But when you take square roots on both sides and you're solving for y, it's just the other option is also possible where you get a minus in front of everything. So if you think of this as a circle, as a single equation, right? When you do this, right, y equals root of 2 minus x squared, that actually corresponds, if you think of the circle as this, like these 2 points as being the equator of the circle, then y equals root of 2 minus x squared corresponds to like the northern hemisphere in a sense. And y equals minus um, root of 2 minus x squared corresponds to like the southern hemisphere. So in a sense, that's another reason why the circle is not the graph of a function. If you want to write it as a graph of a function, you actually need to break it down into two formulas, right? So the upper piece has its own formula, and the lower piece has its own formula um, with the minus sign. Is that making sense? So any questions up to this point? And so once you do that, right, if you say you wanted to find the tangent line, if you remember the original problem, I wanted to find the tangent line going through this point, right, 1 comma -1. If you want to find the tangent line here, this is where the point 1, -1 is, right? So to find the tangent line, basically you can work, so to find the tangent line, you can work with this equation, right? Because this equation is the one that represents the bottom half of the circle. And then to find the tangent line, we need the slope, right? So what's the slope in this case? It is the first derivative, right? So what's the first derivative of this function? Anyone remembers how would you find this? What's the answer in this case? Uh, yeah, you should start. I agree. You should write it first as -2 minus x squared. Oops. You should write it in power format. Yes, that's a good idea. Okay, that actually is useful. And then how do you, what should this derivative give you? In fact, the minus sign that you see here is like just like a constant number, so you can actually take it outside a derivative. So let me just take it outside the derivative to help you out a little bit. And now how do you find the derivative of this expression? Well, I mean, it will, yes, the 1/2 should come down, and then we will lower the exponent by 1, but the question is that all that we take? Is that all that needs to be done in this case, or is there anything left missing? If we only had x, that would be actually, if we had x to the 1/2, what you're saying, um, that would be correct. It's just that this is a chain rule problem because inside the square root, we don't have x. So we have to be careful when we do this derivative. So just to remind you about how the chain rule works, you can put u equals 2 minus x squared. So this is minus the derivative with respect to x of u to the 1/2. Okay. Right, like the idea of the chain rule is that you call the stuff inside the function that you know how to take the derivative of. So we know how to take the derivative of a square root. It's just that the formula for the derivative of a square root had like an x inside. So the next best thing you can do is kind of like just call the junk inside the square root u. And then when you do that, you can do the trick of multiplying and dividing by du. Let me put a different color here. Okay. And the point is that each of these should be easy to compute on its own, because the first one is really just like what we have been saying, like this 1/2 comes down, and then the power of u gets decreased by 1. And then what's the derivative of u with respect to x? That's just minus 2x. So this gives you what? Minus 1/2 u to the negative 1/2 times minus 2x. And that gives you, well, this minus cancels this minus sign, and this 2 cancels this 2. So let me just put it like u to the negative 1/2 times x, and that's x over square root of u. But you can substitute that and replace that u with 2 minus x squared. So that's dy dx. Does that make sense? Are there any questions about this up to this point? So that's the formula for the tangent, for the slope. But if you want the tangent line at this point, right? So this is the slope. So at the point P, which is 1, -1, the slope is, you just evaluate that with x equals 1. So the slope is 1 over 2 minus 1, right? Which is just 1. And the line, and the equation for the line would be y minus -1 equals the slope times x minus 1, right? So this becomes y plus 1 equals x minus 1, or if you prefer, y equals x minus 2. So what I'm saying, back to the circle, oops, let me zoom out, is that if you have the circle here, and you have this point 1 comma -1, the equation of the tangent line at this point would be y equals x minus 2. Is that making sense? Are there any questions about it up to this point? So just to show you this in GeoGebra, how this looks like. So this is x squared plus y squared equals 2. That's the equation of the circle. Let's make it blue because that's like I think the color I was using on the notes. And then you have this point which is 1 -1, right? Which you see here. Let's make it pink. And then the equation of the tangent line, I said it was x minus 2, and there you go. That's the equation of the line. So it does look like the tangent line to the circle. Is that okay? Is that making sense? So so in this first method, the first option was to just solve for y. Okay. Just to recap what I just did. So just to go back on some brief summary of what we just did. So if you wanted to find the slope of the tangent line, what we did in this method, the first option, what I'm calling option 1, was just to take the equation that you were given and just try to solve this equation for the variable y. Okay. There's another option, which is the one that I want to emphasize because it's more convenient, as you'll see, where you're not going to try to solve for the variable. You kind of just remember that the second variable y depends on x. So let me write that down. So like option 2, and this is what is called this is like the method that's actually called implicit differentiation. You do not try to solve for y explicitly in terms of x, instead you use the equation which relates x and y and take the derivative of this equation with respect to x to find the y dx. Oops. Oh, now it's back. Okay, so let me give you a second to copy for you to copy this, and I'll explain what I mean by this with the example with this example. So if you remember, this was the equation that we had, the equation of the circle. So in this second method, you are not going to use this equation to solve for y. That's not the goal. Instead, you kind of work more directly with the equation. And, if you have an equation, there are things that you can do to an equation, like you could multiply both sides of the equation by the number 3, or you could divide both sides of the equation by a number. When you have an equation, you can take square roots on both sides of an equation. You can square both sides of an equation. Well, another thing you can do to an equation is that you can actually take the derivative of both sides of an equation. So what you can do is actually take the derivative of both sides of the equation with respect to, say, the variable x. Is that making sense? So just think of this as analogous to, say, multiplying both sides of the equation by a number. The analog of this in calculus is just like, well, take the equation and take the derivative with respect to x on both sides of it. So far, so good. Okay, now let's start with the easy stuff. What's the derivative of what's the derivative of the right-hand side of the equation? What is that equal to? It's just 0 because remember the derivative of a number or a constant is always 0. There's not much to do. Okay, and then what's the left-hand side? Well, this is a sum, and if you remember, the derivative of a sum of functions is the sum of the derivatives. So just to do this extra step for the first time, let me write it like this. Okay, so I'm just breaking this derivative of the sum into sum of derivatives. That making sense so far, so good? And now let's keep doing the easy stuff first. What's the derivative of x squared with respect to x? Yeah, that's 2x, good. And now comes the tricky part. What's the derivative of y squared with respect to x? Okay, here, okay, let's see. I got an answer in the private chat, which was 0. It cannot be 0. This is where it can be confusing. It cannot be 0 because remember, secretly, y depends on x, right? Right, secretly y depends on x. Is that kind of we're being lazy and we're choosing not to write that explicitly? But in this method, even though we're not writing y as a formula in terms of x, it doesn't mean that it's not a function of x, if you know what I mean. So it cannot be 0 because of that, if that makes sense. So like here, you actually have to think of y as a function of x, but in a way we're pretending that we don't know what the formula is. But that doesn't mean that still there's no relationship between the two variables. Is that making sense? So let me write that explicitly before going on. This is not 0 since y does depend on x. We are just choosing not to find that formula explicitly. Yeah, that's a good question. In this case, like if you look at this formula, y was being squared. Oh, okay. I see. Yeah, it's okay. It will have a dy dx. So now we're getting closer to the truth. So let me just finish writing that this thing first. We are just choosing not to write it. We're just choosing not to find this formula. So to help you, like this is where like this notation is convenient. So as I was saying, just to rewrite this step, this first derivative was just 2x. I think everyone was in agreement with that. To find this derivative, it can be confusing. And so the trick is actually like secretly like a chain rule problem. The trick is kind of to multiply and divide by dy. Okay. And so with the chain rule, we write it this way. And hopefully, when we write it this way, it becomes more clear what the answer needs to be. So let's try to see if that's the case. So oops, what do you think this should be? Good, it's 2y because it, like, what's the difference between this and this? It's essentially that we're just using different letters, right? But like they actually look essentially the same. It's just that here, like the variable is x or x squared x, and the variable here is y squared y, but they actually behave the same way. It's just they're literally, choosing to, at this point, it's kind of like as if you were choosing to write two different letters. write the same equation but in two different letters. So this first factor is 2y, and the second factor is dy dx, and that's what we're after. So it's not, that's okay. We're not supposed to know what that is. So you can just leave that as dy dx. Is that making sense? That's actually the key step in all this problem, to realize that this is actually, you find the derivative kind of in the same way as you would with x. It's just that the answer should be with respect to, in terms of y. And then we're almost there, because you can say that 2y dy dx equals minus 2x. And so dy dx equals minus 2x over minus 2y. So dy dx equals the axis, sorry, like this, right? Minus x over y, right? Is this so far so good of how I got to this equation? Are there any questions about how I got here? So if you compare this, so I'm saying my formula for the derivative is minus x over y. If you compare it to what we found in the first method, right? If you compare it with what we found in the first method, it doesn't look quite the same. But the reason why it doesn't look the same is because in the first method, we did a little bit more because we had y as a function of x as a formula, which we're choosing not to do here. So like the expression for the derivative looks a little bit more weird in this case, because kind of we chose like a path which is a little bit more lazy, because we're not trying to solve explicitly for y. But still, it's good enough. But still, this equation is good enough. But still, at the point at p equals 1 comma negative 1, if you remember, we were trying to find the tangent line at this point. If you, the slope should then be minus x, but now minus x is minus 1 divided by y, and y is now negative 1. Okay, so you see, we still get that the slope is 1, right? So the slope is 1. Which is the same slope that we had found before. You see, so it does still give, it does continue to give you the correct value for the slope after you plug in the values for x and y you're after. Obviously, I'm about to do a second example, which is a little bit more interesting. But is that okay? Any questions about this up to this point? Okay, let's do something, a second example to make sure that this is making sense. Let's go back to GeoGebra first, and I can show you what I want to do now. Okay, let's write another equation. Let's say I want to say write xy plus y cubed equals 10. Oops. Ooh. Okay, let's see. Okay. Okay, now let's look at these curves, like this equation, right? Okay, if you look at this equation, it is quite weird, right? Like how it looks like. I don't think there's even like a specific name for this equation, right? And like I wouldn't like know how to graph it if I didn't have GeoGebra, right? Like, so it is a weird equation, right? But I mean, it should have like tangent lines. So for example, if you take P to be 1, comma 2, okay. If you take P to be 1, comma 2, I mean, it makes sense that there should be a tangent line to this equation, to this curve at this passing through this point. Okay, so what we're going to do now is going to find this tangent line using this method. Okay, so let me write that down on the iPad. So here's example 2. Consider the curve with with equation xy plus 1/4 y cubed equals 4. Yeah. Find the equation of the tangent line through that passes through the point P equals 1, comma 2. Okay. So just as a remark before we start with this equation, so for this equation, if you try to solve for y, that is not an easy thing to do. It's not like the previous equation where it was kind of easy to solve for y in the case of the circle. So in this case, it's not easy to solve for y. So kind of like option 1 is not realistically available to us. In this case, solving for y is not easy or is hard. So option 1 is not realistic. So we need to do option 2. Okay. So what was option 2? Option 2 is literally copy the equation. So it's xy plus 1/4 y cubed equals 4. And what do we do in option 2? We just take the derivative of both sides with respect to x. So let's write that down. Is that making sense up to this point? So far, so good? Okay, and then what do we do here? This is a sum. There's a sum here, so you can write it in terms of the sum of derivatives. And what's again, the derivative of a constant is 0, right? So that's why this becomes 0. Is that okay so far, so good? What can you do to find this derivative? What is that derivative equal to? That's correct if y were a constant, right? But that's a problem in this. That's the problem in these problems that y is not a number, right? It does depend on x. It's just that we are lazy or not capable of writing down like y as a formula, right? But it doesn't mean that y. Oops! It doesn't mean that y is a number. You know what I mean? So yeah, it has to be a product rule because again, secretly, y does depend on x. So you really have to think of y as a function of x, even though we don't know the function explicitly. So, but the product rule does work. So if you do the product rule, remember the derivative of the product rule is the derivative of the first factor times the second factor plus the first factor times the derivative of the second factor. Okay, so let me put that here. This is the product rule. And I'm not going to do too much to this one. I'm just going to pull out the 1/4 because 1/4 is a number. It's a constant, so you can take a number outside a derivative. So let me put this other one like this. Is that making sense? Any questions about this so far? So just be super careful here that you must always think of y as a function of x in these problems, even though you don't have like the explicit formula. Or you must think that y depends on x in these problems, even though you don't have like the explicit formula. So what, just to continue, now after you do this, like things like start getting a lot better. So what's the derivative of x with respect to x? This one can be a little bit weird, but what is this? It's just one. You can use the power rule for that, or actually this is in one of those cases where this notation is convenient. It actually does behave as if you could just cancel the x's. So if you cancel the x with the x, you get one, and it actually works the right way. So it gives you 1 times y plus x dy dx. And now we come to, I mean, there's nothing that we can do with this x, that's just x, and the y dx is what we are after, so it's good that it showed up here. And then we have to find this derivative, and again, this is a tricky one. So what can you do to find this derivative? It's very similar. It's very similar to how we found the derivative in the previous example, right? So what should you do in this case to find this one? It is to break it and use the chain rule, and the chain rule here just means multiply and divide by the y, basically. If you do that, then this one is easy to find. What's the derivative for this one? Good, 3y squared, perfect. It's a power rule. So the exponent comes down, then you decrease it by 1, and then you just, yeah, that's what it gives you. And then that's being multiplied by the y dx equals 0. Okay, so this means that x dy dx plus 3/4 y squared dy dx equals negative y. Okay, like what I'm trying to do now is to solve for dy dx. So if you factorize a dy dx here, it gives you that. Okay, and then literally gives you the equation for dy dx is minus y divided by x plus 3/4 y squared. Is that making sense? Any questions about this? And again, this is a formula for the slope of the tangent line, right? Because that's the derivative. But we want the slope not at a random point. We want the slope at p equals 1, 2. I believe that's a point I had chosen. So that gives you dy dx equal to minus y, so it becomes minus 2 divided by 1 plus 3/4 of y squared. Y squared becomes 2 squared, so this becomes 4. So it's minus 2 divided 1 plus 3, so minus 2/4, so minus 1/2. So n is minus 1/2 at the point p equals 1, 2. So what's the equation of the line of the tangent line? It would be y minus 2, oops, equals y minus 2 equals the slope. The slope is minus 1/2 times x minus 1. And that's the equation. Is that making sense? In fact, well, let me give you a second to copy this and I'll show you in GeoGebra how this looks like. So if we go back to GeoGebra, this was the equation of the line. This was the point 1, 2. And the equation, I'm saying, sorry, this was the equation of the curve, right? This is the point 1, 2. And I'm just saying that the equation of the tangent line should be y minus 2 equals minus 1/2. So minus 1/2 is minus 0.5 times x minus 1. And let me put like a different color, purple, and make the curve blue. So you see, like it does look like the tangent line, right, at this point. So it does work. But the interesting thing about doing it this way is that at no point, the cool thing about this method is that at no point did you ever find y explicitly as a function of x. You see? But still you can find the derivative, even if you don't know the formula for y. Is that okay? Okay, so this is more or less what I wanted to tell you about this method. The next thing we have to do still is related to this, but it's slightly different. So let's take like a 5-minute break, and then once we come back, I'll tell you about the other stuff, which involves inverses of functions, and that's also interesting. Okay, so yeah, let's take a 5-minute break, and we'll start talking about that then. Uh, Okay. By the way, because someone asked me about homework deadlines, usually the way I have the settings on my lab, it allows you to do late submissions and you don't lose any points. So it's okay. The deadline is more like as a recommendation by when you should be done with the assignment, but you shouldn't have any problem like continuing the assignment after the deadline, and you won't get points taken off. If still someone is having an issue, you can email me. But if it's working fine, then yeah, like the deadline, like you can just continue working on it after past the deadline. So okay, so now we're going to talk about inverses of functions. And it's going to be related to what we're doing here. You'll see in a second. So let me remind you quickly about what the inverse of a function is. So for this, it's kind of nice to have like the diagram view of a function. So if you remember, I had told you could think of a function as a machine. So like the idea of a function as a machine is that you feed into the machine like the number x, right? And it will spit out the value of the function evaluated at x, okay? So for example, if your machine, right? If your machine is like the x cubed, right? Oops. Then the idea of the function x cubed is that you feed into it x, right? And sorry, well, it will spit out x cubed, right? That's the idea in this case. So more concretely, like for example, if you were to feed the number 2 to it, right? Then the output that it gives you is 8, right? So that's how the x cubed works if you think about it as a machine, right? It receives an input and it gives you an output. So far so good. Uh, so the idea of the inverse, like if you look at these diagrams, that the machine has like a directionality, right? It starts with 2 and it spits out 8. Okay. So the idea of an inverse is that kind of it's like the machine run backwards, right? Like so the inverse of a function is a machine played backwards. Like if you thought about it as a movie, you're just going in reverse, playing it backwards. Okay, so for example, for the case of x cubed, right? Well, the idea is that the arrows just run in reverse. So uh, that means that if you were to feed 8 to this machine, which was the output before, now this is the input, and in return you get the input from before, which is the new output. It turns to 8 into 2. Okay. So you see, like the difference between this one and the inverse is that like the output becomes the input and the input becomes the output. Is that making sense? So it's like it's flipping reversing the roles basically for what input and output is. And in fact, there is a name for this inverse function, right? So more generally, right? the idea of like the inverse of x cubed is that it's reversing these two roles. So if you fed to it like a number like x cubed, right? What the inverse of x cubed will spit is x, right? So what's there's like you probably learned like a long time ago, like the name for a function that does this. What's the name of a function that has like this property? How could you start with a number which is like x cubed and obtain the number x? What could you do to that number? And yeah, the cubic root of x, that's basically how it's called. So let's call this function g like the inverse of x cubed is cubic root of x, right? So the idea is that if you take like a number x, the cubic root basically gives you cubic root of x, the cube root of x. And like if the number that you had fed to it had been x cubed, right? Then it would have taken the cube root of x cubed, right? But that's just x. So that's like why this diagram is the same that you have here. But what I'm trying to say is that many of these inverses, they have names that they're kind of familiar functions, but like you have to think of them as undoing, the effect of a function from before. Okay. So like more generally, like this is what I'm trying to get at. Like in general, f inverse of x is the name for the inverse, is the name for the inverse of f. Yeah, this can be confusing. It should not be confused with 1 over f. Okay, so this is important. Like, of course, it can be confusing. So it's like, it's not the same as 1 over fx. So it is like in the sense, it is like a unfortunate accident that um, it looks like 1 over f of x, but it does have like a different meaning. So the idea of like the inverse of like the function is that if you have like again, if you have like an input x that spits out the output f of x, then the inverse, what the effect of the inverse is that it eats out, if you feed f of x to it, it would spit out x. So it's undoing the effect of the function. So it's really like the machine run backwards, which is not necessarily the same as 1 over f of x. Is that making sense? So sometimes you have to be careful, right? So sometimes you have to be careful. So for example, imagine that your function had been x squared, right? So what's the problem with x squared? Well, the problem with x squared is that actually sometimes different inputs can go to the same output, right? So for example, if you take the number 2, right? Let's put it here, f of x, x squared, f of x, x squared. If you take the number 2, right, it goes to 4. But if you take the number -2, it also goes to 4, right? So if you wanted to run the machine in reverse, right, the input would be 4 now, but what should be the output? How do you decide what the output is? So the convention, like in that case, is that for like something like x squared, that x squared, like you take the inverse whenever you're considering values for x that are non-negative, right? So when you say that the square root, like the inverse of this function should be x a square root. So inverse is going to be square root. But when you talk about taking the inverse in this sense, for example, if you fit 4 to it, the convention is just to choose always a positive value. Otherwise, we would have two choices if that makes sense. So the convention is to choose like the positive value for it. Is that making sense? So sometimes when you, for certain functions, you can still kind of find their inverses, but when you do that, you have to make a choice. So to clarify what you mean by the inverse, because sometimes there could be multiple options, if that makes sense. Is that okay? Any questions about this? So there's a very important function that, so in general, we can find the derivative for the inverse of the function, but let's just start with some examples first. So some remarks. The inverse of f of x equal to x to the n, right, will be f inverse of x, which is x to the 1 over n, or the nth root of x. Okay, that's one. And the inverse, so that's one important inverses to know. Another very important inverse to know is the inverse of the exponential function. What's the inverse of, anyone remembers the name for the inverse of the exponential function? It's called the natural log, yes. The natural logarithm. And the way in which we will write it in this course is ln of x. So again, what that means is that just to make the diagrams, if you like them, I don't know. If you start with x and you get e to the x, right? If you use the exponential function, then the inverse runs in reverse. So the inverse takes e to the x and gives you x. So like, in fact, just to be more precise, what's happening here is that if you give e to the x to the inverse, it's going to output you the natural log of e to the x. But that's just, it's supposed to be the inverse. So like the idea is like the natural log cancels the exponential and that just gives you x. Or more generally, yeah. You can think about it as a function of x. So it spits out the input is x and it gives you ln of x. Is that making sense? So like that's how you end up with this like equation, which is very useful, that ln of e to the x equals x, and also e to the ln of x is also x. So those are two important equations to have. Is that making sense? So now the cool thing is that we can use the implicit the method from before to find the derivative of the natural log. Okay, so for example, we can now, the idea is that we can use the method from before So how can we do that? First, like um well, in this case, I'm going to assume that we already know the derivative for the exponential, which I had already given to you. So the idea in this equation is that actually first we make the exponential appear. Okay. So let me see if I can say this in a useful way. So like in this equation, so we already know the derivative of the exponential. So I mean, there's another thing you can do with an equation, which you may have done in the past, is that you can exponentiate both sides of an equation. So you raise each side of the equation to, I mean, you do e to each side of the equation. E to the y has to be the same as e to the ln of x. So you use each side of the equation as the power of e, basically. Is that making sense? But then what is, I mean, e to the y is just e to the y. We don't really know that. But what is e to the ln of x? E to the ln of x, if you remember, the idea is that whenever an exponential sees a logarithm, they kill each other. So they kind of like disintegrate. So you just get back x. And then what we can do is take the derivative of both sides with respect to x of this equation. So that's where this is very similar to what we were just doing before in the previous examples of today. Okay, so what is this supposed to be? This should just be one, right? Because it's like as before we had been doing before. Okay. And then how can you find this derivative? There's a trick that we have been using, right? What can you do to find this derivative? So you sorry, you multiply and divide by the y. So you get that. But now, what's the derivative of e to the y with respect to y? Better to think about it in words. What's the derivative of the exponential function? Well, it's just itself. The derivative of e to the x is e to the x. So by the same logic, the derivative of e to the y with respect to y is just going to be e to the y. So actually, these just gives you e to the y again. That can be a little bit confusing, but you just get the same answer. So that means that the derivative for dy dx is 1 over e to the y. But what is e to the y? E to the y is x. So you get 1 over x. So that means that the derivative, and finally we get to the important thing. So this is like the important result. The derivative with respect to x of the natural log is just 1 over x. Is that making sense? Or ln prime of x equals 1 over x if you prefer. So let's do another example to make sure if this is making sense. So the derivative of the exponential is called natural log. The derivative of the trig function, sorry, the inverse of the exponential is called natural log. The inverse, here's another example. The inverses of sine of x, cosine of x, tangent of x, secant of x, well, let me put it like this, cosecant of x. Secant of x, cotangent of x are called, you just put like an arc in front of them, so it's called arc, arc sine of x, arc cosine of x, arc tangent of x, arc cosecant of x, arc secant of x, arc cotangent of x. So for example, what that means is that if you had like, just to give you like this more pictorially, if you had here x that gets sent to sine of x, right? If this is like the function sine of x, what arc sine does is undo this function. So arc sine of x, like if you feed sine of x to it, like arc sine kind of vanishes the sign. So arc sine of x kind of cancels out the signs. So it just gives you back x. So you see it takes sine of x, it takes sine of x as the input and returns x as the output. So in that sense, that's the sense in which is the inverse. It kind of undoes the effect. So again, it's kind of like you have like you end up having like arc sine of x equals x, or sine of arc sine of x equals x, and then you have and you know that you have like arc cosine of x equals x, and cosine of arc cosine of x equals x, and then you have the same for the others. So like arc tangent of x equals x, or tangent of arc tan of x equals x. Okay, and then you have like the same for the other three, like arc secant of x equals x, or secant of arc secant of x equals x, arc cosecant of x equals x, cosecant of arc cosecant of x equals x, and finally arc cotangent of x equals x, or cotangent of arc cotangent of x equals x. Okay. So let me just write this down and I'll do it tomorrow, but just I'll give it to you for you to think about. So here's something for you to think about for tomorrow, and I'll do it. So think of it as a homework. I won't grade it or anything, but just like for you to try. So here's something for you to try. Let's say what's the derivative? Let's say I want to find what is the derivative of y equals arc sine of x. Let's say I try to find the derivative of arc sine of x. So essentially if you want to do that, start by taking sine on both sides of the equation. what is sine of arcsine of x? I wrote it earlier. Earlier is just x. So you and take the derivative of both sides. So you get sine of y equals x, and take the derivative of this with respect to x. Okay, so try to do that for tomorrow. So it's very similar to what we were doing a couple of minutes ago with the exponential and the logarithm. Now we're trying to do it with sine and arcsine. So try to figure out for tomorrow if you can find like a starting from here, you can kind of like find like a formula for the derivative of arcsine of x. You can check the book. It's written there, but try to do it on your own. And tomorrow I'll tell you what that is, how to finish these steps. But I think it's a fun exercise for you to try to see if this is making sense. So tomorrow we'll keep talking about this and probably start talking about related rates. But yeah, I think it's a good place to end because this has been a lot of information. So I think
Professor, before you go,
Mhm.
tomorrow's my birthday. Is there any way I can postpone the quiz?
Well, the quizzes like I'm doing them so that they're each one is 9 points. So that's basically so that can people, each one should be 6 points, but by making them 9, then you can get extra points, and that makes up for lost quizzes. So I'm just trying to say that if you don't take the quiz tomorrow, then you should be fine because the remaining quizzes have X points above the minimum for each quiz, if that makes sense. So you can miss it
Okay.
without any problems. But yeah, I'm not putting makeup for the quizzes, but because it's easier to do that. It's kind of like a drop down policy. Because
But with
there are
extra
10
points.
right, there are 10 quizzes on this course. I think that's how I was planning on it. And only 60 points, but each quiz is worth 9 points. So you can end up getting up to 90 points, you see. But anything else, anything above 60 kind of like doesn't, once you hit 60, it's kind of like the ceiling, so you're done.
Okay,
So yeah,
thank you.
yeah, sure. If you miss, yeah, enjoy your birthday. If you miss like a quiz, that's fine. Like you make it up with the other quizzes.
Have a great one.
Okay, you too.